So, all right. So now we can actually begin. Now that we have some clue as to how to add vectors, we can begin the process of analyzing, or the vectors that we know. Like, for instance, how do you actually write the vectors that we know? What are the first vectors that we learned in this class? Yes? No, the first vectors we learned in this course. What? You guys, velocity of position. So the position vector. Does anybody know what the position of a particle is? Okay, but what does it mean? It's a point. Point with respect to? You might need to go back to Unit 1, yes. That's right. So in other words, you define an origin, and what is the position of a particle? A point with respect to that origin. So then, how do we do that? So then what would the position vector correspond to? So naturally, I need ruled lines. And here's my x-y axis. Okay? So what would my position vector correspond to, guys? Well, first I need an origin. So here's 0, 0. So what do? What is the position of an object? It is a vector that extends from the origin to some point in space. I didn't mean to do that. So this is the position vector. Or if you want, what I could do is even something a little bit more drastic. Let me have this thing move all over the place. In other words, here is this object, here is this fly, and what the fly is doing, it's traveling like that. What the fly is doing is traveling like that. And of course, this is the y. This is x. And notice what's not described in this. Oh, clearly. But what else? Okay, the velocity's not described, but what really is playing out? Like, clearly it can't be in all these places at the same time. Time. So time's not described, it's implicit. What it means is that this is some earlier point in time, and this, maybe I should have an arrow, and that is some later point in time. So this is at T1, this is at T2, and so on and so forth. It just goes to show you the difficulty of moving towards a more than one dimension. When you actually start describing things like where the position of something is at a point in time, you won't get those clean graphs that we had in the first unit. They're almost kind of effectively meaningless. So then let's call this some point T. So then if you look at this position, what does this describe? This describes some R of T, where R represents what's called the position vector. So notice R of T1 is not equal to, I don't know, R of T5. Here's T5. They're just not the same position, right? They're in very different positions, in fact. R of T1 corresponds to this guy. That's R of T1. R of T5 corresponds to this guy. So what we can do is we can actually what's called parameterize this. Namely, keep track of where this thing is moving in time. But how are we going to do this? Well, if you take a look, what direction is r in? See if you guys can actually infer which direction r is in. At all points in time, which direction is r in? Yes? Close. You're so damn close. You don't even know it. Instead of saying up, say out. It's in the outward direction at all points in time. So what does it mean to be in the outwards direction? That means we're no longer in Kansas, or what we call the Cartesian plane. What coordinate system are we in when we talk about out? Was it? Out versus. So I don't think you guys have much experience with this, so I'm just going to kind of give it to you. It's called polar coordinates. In polar coordinates, what you have is instead of your x direction, y direction, you have your r direction and theta direction, which is perpendicular to r. So if you look at the position vector, which way is the position vector always directed? Outward. Like, for instance, r of t5 is directed this way, which is radially outward. Similarly, r of t1 is directed this way, which is radially outward. And someone very wise is looking at this a little confused. Why? Because they're noticing that the unit vectors are changing depending upon where this position is. And that's right. We're not in Kansas anymore. In Kansas, otherwise known as the Cartesian coordinate system, your unit vectors always point in the same direction. In other words, which way does I hat point? That way. Which way does j hat point? That way. But notice if you're here, r hat points this way and theta hat points this way. But if you're here, r hat points that way and theta hat points that way. So this is one of the complications that comes with polar coordinates, namely that the unit vectors change with time and with space as well. But anyhow, they still have a magnitude of 1, and to some degree we don't need to deal with them just yet. We'll wait for a later date to tackle transforming back into polar coordinates. For right now, what I want to do is I want to express the position vector. And so to describe the position vector, r of t, it's simply equal to, it's not exactly defined, but it's equal to the magnitude of r of t in what direction? In the r hat direction. Notice there's no component of the position vector that is not in the radially outward direction. It extends from the origin to some point in the plane. But what can we do with this? We can transform this into Cartesian coordinates. How would we do that? Well, you take r of t and you break it up into its vectors. What are the two components of this? X of t and y of t. And so what can you say r of t is equal to? X of t I plus Well, that's nice. It's really nice. And we can do this at every point in space or every point in time. Any questions on this? But now there's a feature to the position vector. Hello.
Pictures of them while you're teaching them?
Sure.
Try not to look at me.
So the position vector, there's a problem with it. Anybody want to identify it? What's the problem with the position vector? Take this room and take my movement in this room. Andrew and Casey, right? Would you record the same position for me? Yes or no? No, what would you record? Would you guys register the same position? Yes or no? No. You would register a different position for me than you would, correct? So now, what about if I moved from this position to this position? Would you guys agree on the position vectors? Yes or no? Yes. The answer is no. But what would you agree on? Who said it? No, someone said the right answer. The displacement. You would agree on the displacement. So let's show that. Now that we understand that displacement is independent of the origin of your coordinate system, we can now begin looking at all of our dynamic variables. Because we have that R of t, just got way too large, is equal to x of t I hat plus y of t j hat. So we can actually write this in terms of final and initial as well. We have it as a function of time in general. So RF is equal to xf I hat plus yf j hat. And similarly, Ri is equal to xi I hat plus yi j hat. And what did I just do here? All I did was take this vector. I can erase this coordinate system now and just look at this coordinate system. Maybe I'm better off just redrawing it. This is Ri, this is Rf, right? All I'm doing is I'm taking Ri and decomposing it into what? Its components, xi, yi. And similarly, xf, yf. And what do you notice? This displacement vector, which goes like that, is equal to what? It's equal to this vector, right, plus that vector. And if you notice, what is this vector? xf minus xi. And what's this vector? And so there you have it. So therefore, delta R is equal to xf minus xi I hat, right, plus yf minus yi j hat. And right now, you're actually getting a feel for what this whole unit's about. Namely, what happens in Vegas stays in Vegas, right? So, what does that mean? Everything that happens in the y direction stays in the y direction. Whatever happens in the x direction stays in the x direction. And you better thank your lucky stars for it. Because if it didn't, life would be a hell of a lot harder. So delta r is then going to be delta x I hat plus delta y j hat. And so now what can we define? Once we have displacement, we can define what velocity? Average velocity, right? So you can say average velocity in the r direction, in the radial direction, is defined as delta r over delta t. But what's that? That's delta x over delta t I hat plus delta y over delta t j hat. But what's delta x over delta t mean? What is that? That's the average velocity in the x direction. So we have VR average equals Vx average I hat plus Vy average j hat. That should be an R. Now that I have average velocity defined, what can I define with it? No, not yet. You need instantaneous. So how do you define the instantaneous velocity? In other words, what is VR of t? Be careful. Be careful. It's the limit as delta t goes to 0 of the what quantity? Of the average. Or in other words, right, of But what's this? Huh? No, that's definitely not undefined. This is definitely defined. You're saying that delta t is 0, but it's not 0. It's going to 0. That is the what type of velocity? That's right. In other words, VR of t is equal to Vx of t, I hat, plus Vy of t, j hat. In other words, it's the instantaneous velocity in the x direction and the instantaneous velocity in the y direction. Now what can we do? We can define which acceleration? Average acceleration. How do we define average acceleration? Same exact way. You have a final instantaneous velocity in each direction, right? So you can call this VRF equals VXF I hat plus VYF j hat. And you have a VRI Notice, why do I keep on saying R? What does that R stand for? Radial or resultant. So this is VRI, which is VXI I hat plus VYI j hat. And from this, what are you able to derive? Definition of average acceleration. What's the definition of average acceleration? That's right, VF minus VI over delta t. Right? But what's VF minus VI? That's going to be VXF minus VXI I hat plus VYF minus VYI J hat. All this over delta T. That delta T distributes to each term. Notice what's this? No. VF minus VI is delta V in what direction? And there you go. And that is the average acceleration in the radial direction. Of course, this is equal to the average acceleration in the, what's that? X direction plus average acceleration in the Y direction. And of course, if I wanted to define instantaneous acceleration, what would I do? Take the limit as delta t goes to 0. Any questions? This is the time to ask. Notice, what do we have? What is this outline? Complete independence of the x direction and y direction. Independence of x direction and y direction. What happens in y stays in y. What happens in x stays in x. I think, all right, so relative velocity. And this will actually be the last little bit before we go into projectile motion. So relative velocity. Now remember, I gave a definition for relative velocity before, right? What was that definition? Do you guys remember? I said if you have two cars, car 1 and car 2, car A and car B, the velocity of A relative to B is equal to what? Yes. Correct. And so now the question is, do I have to change anything? So the way we determine this is, I don't know if you remember how we derived this. We derived this based on a physical situation to make it consistent with what our observations were. So now let's actually make an analogous situation. So let's see if this actually holds water. So now it's enormous, and oh God, 25, and select that, delete it, put it up to 200, and now we're good. So let's take a fairly simple but general situation. You have a car, right, that's moving to the east at, say, 50 miles per hour or kilometers per hour. And you have another car that is, I don't know, south of it, that's heading north at 70 kilometers per hour. And let's call this car A, and we'll call this car B. So now, do you remember how we derived this? What does the velocity of A relative to B physically mean? It is the velocity with which A sees B, B sees A. And remember, this whole framework was rested on the notion that B sees itself at rest. It sees itself at rest. So if B sees itself at rest, what does it see A doing? It sees A going to the right at what velocity? 50 meters per second, right? Or 50 kilometers per hour. What else does it see A doing? Coming south at 70 kilometers per hour. And so now, does this describe that situation? In other words, what does B observe A doing? Moving in which trajectory? And this should be the velocity of A relative to B. Well, let's see. VA, so we draw our coordinate system. Okay? VA is equal to what in our coordinate system? 50 I hat plus 0 j hat. VB is 0 I hat plus 70 j hat. So then let's see if this definition holds water. So what's VA minus VB? So V of A relative to B should be 50 minus 0, right, plus 0 minus 70. That's I hat, and that's j hat. So in other words, it's 50 I hat, right, plus negative 70 j hat. Is that what we observe? We're in good shape. So we don't need to change a damn thing. We're good. That's it. I mean, literally, that's it. Now it's just a matter of solving problems. Like, you know, you have a river, river's flowing. Okay? You hate these problems? Of course, because you had no physical... They're physics problems that they're forcing math solutions to. And if those solutions in math involve kind of memorizing a set of algorithms without understanding it, then it's going to be hellish. So let's suppose that the river is, I don't know, moving east at 10 meters per second. And you can row north at 3. You can row north at 3. VA equals 3 meters per second. And let's suppose the river is 100 meters wide. And the question is how far from your starting point will you end up if you end up rowing just directly across? So what would you do? You'd find your resultant velocity. Well, if you take a look, you have independence here, right? And instead of 3, I'll make that 5, just so the math's easier. So how much time does it take you to row across? 20 seconds. So it takes 20 seconds to row that 100 meters, right? And then in those 20 seconds, you're moving 200 that way. And so this is kind of a classic, straightforward problem. Now, if I were to ask you, which way should you row to end up directly across? Yeah, you should row this way. But it may not even be possible. It may not be possible to end up directly across. Why? Well, correct. Does everybody follow this? So is it possible to get across, directly across? And the answer is no. So you have to be a little careful. And really what this is asking, yeah, because if you go any amount, any angle, you're still going to be going over 5 meters per second in that direction. That's right, in order to get to this point directly across. Correct. So that means you're going to be hauling that